Hello everyone. So following up with what we've been doing previously, or what we have done last in the last video. So there are a few things that we have covered, and we've done several exercises on slopes and distances between 2 points. Um, so to quickly have a go on this, we have we've done a couple of linear equations and. With linear equations, usually have them in a form where y equals m of x. M is the slope and x is the points or whatever it is, the value. Yeah, and then when you have a plus b or c based on the convention that you use, that c or b is the y-intercept, where the line crosses the y-intercept. Usually m of x m multiplied by x means the y-intercept is 0, which passes through the origin. And we have done we can calculate the slope based on the formula delta y, the change in y over the change of x. And if assuming we have the slope, we can easily calculate the y's. And in a point slope form, when you have 2 points, you can easily use the following function and solve accordingly. There is also the standard form of the equation, and it's basically the same form as y equals m of x of b. And then you can see here that y, it's like ay minus or plus m of x minus b equals c, or equals 0. So this is the standard form, and we've done a couple things on. And we were also introduced to the distance between 2 points, in which you can calculate the change of y over the change of x, and then you get the slope, the distance. And then the distance is actually the square root of b squared plus a squared. The change of b and the change of a, you have 2 points here, so you have y minus y b and xa minus xb. And following on the lessons that we've looked at, so we've looked at we have perpendicular slopes to each other. You have p over x, and then you have minus q over because that simply changes the okay. So these are just solutions to common problems. Now, moving on, now that we're familiar with the linear equations, we can move on to more complicated solution systems in which you have more than one equation or more than one line. Um, and like in this case, if you have two equations, y equals to x and b, so these are two different linear equations. So there has to be a point where they intersect, and that point usually is denoted by solving one for the other. So you could go like x would equal half of y, and then you would replace x with half of y with 2y here in the original equation. Then you get a value of y, and then that value you would replace it on the function, and then that's the point where they intersect. Now, not all equations do have an intersection point. Not all systems have a single solutions like this one. Some systems do not have a solution. Usually you can think of them like when they are parallel to each other. And then there are systems with many solutions, not a single point, and you can think of it as two overlapping lines, one on top of the other. And then you have these two systems, these two equations like this, and then you try to solve one for the other. You have two methods of solving these such systems. One is called substitution and one called the elimination method. In the elimination method, you line them up together like this, and then you subtract one from the other. So this way, for some reason, this is done the addition. I thought it was actually the subtraction. Oh, okay, so you always add, but sometimes when you need to get rid of so once we've done the addition, that's how we get rid of the y's, and then we'll just be left with the x's, and x would equal 18/3, and that's we get 6. Um, yeah, so we have different solutions like this one. If we have a different solution like unlike the one we've seen at the top, what we can do is that, you could actually, it's actually subtraction, so this is the first step. Okay, then I was in one variable and add the function. The above example we could multiply. Yeah, so these are two different ways to solve this problem. And if you want to get rid of the x, you could multiply by -2x. This would be plus, and this would actually be 6, because you're multiplying by -2. And that's how you solve for both. So you eliminate one equation, you create a part of the equation. Nice. So that's the intersecting point. So this is it forms a new equation where the function of this equation is the result we've obtained here, 9y equals 9, whatever the value is. Yeah. Multiplying an equation with a constant does not change it, but addition or subtraction or so that's why we multiply, because multiplication really doesn't change what doesn't really change the value that we're working with, working with. So we have the subtraction and elimination, and then we could, as we've seen, so there's a substitution and elimination, and these are basically what I've been telling you. So there is a one solution, we call it a consistent system, and no solution is an inconsistent system. An infinite number of solutions where the lines basically overlap, we call it consistent. It's also a consistent system dependent equations. Apparently we can detect from the get-go if this sort of system is actually solvable, consistent or inconsistent, because if you have two equations with the same slope then and different y-intercepts, then you have a single so different y-intercepts and same slope. Above means that the lines are parallel. We can see that the slope is the same but different y-intercepts, so the above is inconsistent, no solutions. So it's all based on the slope. In both equations, then the solution can intersect at some point. The solution would be consistent with the independent equation. So we should add that to Anki. I'll add it here. The reason why there aren't any solutions for parallel equations is that when eliminating one variable, the other gets eliminated as well, and hence the result doesn't really make any sense. You can see here the answer is a contradiction. 0 doesn't really equal 4. It's inconsistent. The answer is the same if you opt for substitution as well. Yeah. When the system has many solutions, you will end up with the following. So you'll end up with the following. So can you tell? So if you multiply by 2, so this is the summary. Unique pairs. Okay. Similar to the two-pair variable equations, Duvel can have many solutions. One intersect point where the planes meet. If two or more planes are parallel, then you have a line that connects them. If they overlap, then you have a whole plane. If two planes are parallel, then you don't have a solution because there's no point shared among the three planes. Basically, it's the same as the linear equation. It's basically the same as the linear equation deal. And then you could see here that could see here that, for example, why this is not true, because there are no solutions for this one, because not the three planes should meet at some point. And in this case, you have 1 and 2 meeting, but 2 and 3 not, but 1 and 3 separated. And the same here. So you have these two connected at this point, but these, they're connected to the, this horizontal plane on different points. And that's why it makes the equation without a solution. And if you can see here, when the three of them share the intersecting points, that's when you get many solutions. And then when you have them combined at some point, all of them meet at a point, then you can safely say that the system is consistent and it has one solution, consistent basically. Yeah. Solving two variable equations can be done using either elimination or substitution, just like we've seen. So in that case, you would take, say for example, you have three linear equations. You would solve two, and then take another distinct two, and then the answer solve it together. And it would generate a new equation with two variables. Those newly created equations would then be used to solve the system, mostly as described using elimination. If a system produces a single solution through elimination or substitution for each variable, then it is a system with a single solution. If we are solving a system and we obtain an equality, then the system has many solutions. But if you get an inequality, then you're basically solving a system without solutions, a parallel system basically. So in this case, when you get 0 equals 0, then you get many solutions. But in this case, it's contradicting. Then the systems do not meet at a single point. And yeah. And that's what we have covered so far, the systems. Let's try to look for exercises and solve them. So I found this site that I think that could be useful in solving some equations of solving some linear equations. So let's start here. It says solve the system of two linear equations and check the solution. So we need to connect both ends. Is that right? Check solutions. That's weird. Alright, let's see. Let's see what we've got. So when we add these together, so we have 2x equals 6. x actually equals 3. So let's see the solutions. Where are they? Oh, it's kind of funny that it's displayed in this manner. Well, it's better than nothing. Let me just give me a minute. Let me try to look for other possible prospects and see. Okay, this looks like it's a better site. SHMOOP. Okay. All solving systems of linear equations by substitution exercises. Okay, so this is more like sub by substitution. It says that it's substitution, but we really don't have to stick to substitution. And I think it's best that we use a paper and pen, but let's see if we can solve these directly. Okay, so we know these, like we could move this to the other side. Then we will have x plus. I need to get a paper and pen. Just give me a sec. Okay, so we will stick to the question. So they've asked us to solve using substitution. So let's do that. So we've got 5 plus 2y equals x minus 3. That's on one hand. On the other hand, we've got 3x plus 2y equals 11. Now, using substitution, what we can do is that we could have the first one would be x equals 8 plus 2y, right? Right. So we substitute x in the second equation. So we have 3 multiplied by 8 plus 2y okay, 2y, 8 plus 2y, great, plus 2y, not bad pen, okay, so it's 2y equals 11, get another pen, this one is dead. Alright, so we're back in the game, so we've got that, so we're trying to solve for, okay, so and then we should multiply the 3 in the brackets. So 3 multiplied by 8 is 24. 24 plus 6y plus 2y equals 11. And then we have 6 and 2, that's 8y. 24 plus 8y equals 1. And then if we decided to move the 24 to the other side, then 8y equals negative 23. And then if 23 divided by 8, let's just stick to y equals 23 divided by 8. And then what we could do is that we're looking at divided by 2. I don't think there's a... Okay, so let's see the answer. So we've got 23. So oh, my bad, it's equals to... So I've been solving the equation 24 plus 6y plus 2 equals 1. It actually equals 11, so that's my bad. That's a wrong solution for us here. Moving on to the second equation. So we need to be a bit faster now. We need to move like a super turbo flash speed. 3x minus 1 equals 4. And then we have 7x plus 9y equals 32. So if we try to substitute the first equation in the second one, let's try to solve for the first one. Let's have y equals 3x minus 4. And then we substitute that in the second equation. So we have 7x plus 9 multiplied by 3x minus 4 equals 32. And then when we multiply the 9 into the equation, we have 7x plus 27x minus 12 equals 32. If we move the 12 to the other side, then we will have 44. So this would equal 44. And then we will have 7x plus 27. So we have 27 plus 7, that's like 34. 34x equals 44. So x would equal 44 divided by 34. And that's like 44 divided by 34. We have the, if we can multiply it by 2, we probably get 22. 34 if we divide it by 2, then we get 17. So this is like 22 over 17. So this is the x. 22 over 17, y would equal 3 multiplied by 22 over 17 minus 4, right? So we've got 3 multiplied by 22, that's like 66, I guess. 66 out of 17 minus 4. Interesting. So if 66 is divisible by 17, what if we divide 66 divided by, I don't know. Anyway, so what we could do is that we could unify the denominator. So we could have 17 multiplied by 4. It's like 68 minus 66 minus 68 out of 17, right? And then that's like negative 2 out of 17. Let's see. So we've got 22 over 17 for x, and for y, negative 2 out of 17. Oh my god. What have we done wrong? Probably done a lot of things wrong. This is actually 2, 2. Alright. Let's try to solve for the other one. Should be rather straightforward. We got y equates to y equals negative 11x plus 1. Then we have 33x minus 5 equals minus 2 minus 3y. Okay, so we have the y, we have our y. First of all, let's try to minimize the second equation. So we have 33x equals, so 5 goes to the other side, that's like plus 5 minus 3, that's like plus 3. It's like 3 minus 3y. And then we substitute the y, so we have 33x equals 3 minus 3 multiplied by negative 11x plus 1, right? Yeah. So if we multiply the 3 within the bracket, so we have 3 minus 3 is plus 33x plus 1, which equals to 33x. Then this would equal to 4. 4 plus 33x, 33x. If we try to move, we'll have 0 equals, so no solution. This linear system doesn't have any solution. These are the same lines, so not really the same line, it's more like a parallel. So every point on the line is a solution. It's weird. It really didn't equate it on my end. I'm not sure if you guys had the same. It's really weird. Am I answering these questions? Alright, let's try to solve example number 4. Okay, so we could like try and give it the substitution, the elimination method, and see if it really solves the equation for us, to really decide if we're doing anything wrong in our solutions, or that these guys use a different convention to what we've learned. Anyway, so y equals negative x plus 7. That's pretty clear to us. And then let's try to solve this for the second one. We have y equates to y. So let's directly substitute the y with the value we've got. So it's minus x plus 7 plus x would equal to 0. Okay, so it's 9 minus x plus 7. So it's not, so that's not, is there a negative sign in front of the 7? No, it's not. So 9 plus 7. It will be like plus 6. So let's do 16 minus x plus x equals to 0. This has absolutely no solution. Don't tell me it's in the same line. The system has no solution. Now it's weird because on the first attempt that we've tried to do, I'm probably missing something here. Oh, it's minus. Sorry, it's actually minus. So 3 minus 3 is actually 0. So in the previous solution, I've actually done a mistake here. I found out what my mistake was. It was actually in the multiplication. I forgot to really multiply the number and the negative sign into the equation that we had. So it's actually in the same line. Awesome. So let's do one more equation and then try to skip this one. Or we could do maybe more. I don't know, because the side that I've been wanting to check, maths is fun. It's not really responding anymore. Their servers are down or something. So hopefully we'll check it back later. Okay, back to what we're doing. So I think we're in problem number 6. Was it 6? What was our last solution? Yeah, let's just do 6 straight away. Let's just jump into 6. So we have the following equation in which we have 1 over 3x plus 1 over 4y equals 3. And then for the second equation, we have 2x minus y equals to 4. So let's try to simplify the second equation and change it to a form that really makes things a lot easier for us. So we have 2x equals 4 plus y, right? That's 2x for you. But you know what? Let's just have a y. Y equals to, so we have 2x minus 4 equals to y. So we have this first equation, and then try to implement the second and the first equation. So the first equation says that 1 over 3x plus 1 over 4 multiplied by the y value that we obtained from the second equation. So it's 2x minus 4, which equals to 3, right? Awesome. So let's multiply the quarter into 2x plus minus 3. So we have 1 over 3x slowly and smoothly so that we don't mix anything up. So we have 1 over 2x minus 1 over 4, like minus 1, which equals to 3. So 1 over 3x plus 1 over 2x would equal to 4, right? And then we would unify the denominator and try to solve accordingly. So we have this 4. So the first one would be 2 over 6 x plus 3 over 6. X equals 4. And then so we unified the denominator, so it's 5 over 6x, which equals to 4. So x would equal 4 multiplied by 6 over 5. So that's like 24 over 5. 24 over 5, and that's that. And then we multiply that in the y. So we will have 2 multiplied by 24 over 5 minus 4. That would should give us the y. So that's like 48. 48 out of 5 minus 4 will give us the y. So if you unify the denominator, 48 minus 20 out of 5, that gives us the y. So we have 28 out of 5, 28 out of 5, that's the y. So we have 24 and 28 out of 5, of course. Out of 5, sorry. Yeah, so it's 24 out of 5 and 28 out of 5. I think we've got a good handle of this and how we could be solving these equations. So I think we've done a good chunk of exercises in this topic precisely. What we could do is that we could, that's weird, we could, what we could do, like this guy is now, oh, it's actually back online, so we could really go through this really quickly and see if there's anything else we missed. And there are sets of exercises on the bottom, so we could on the very bottom, so we could really use those to solve more problems. Let me check how much time we've got. Okay, so I think we could go through this and then we could dive deeper into. It's interesting. It's quite a lengthy subject that we could cover in a whole video, on a video on its own. So yeah, let's leave this one for the second video. And yeah, it's a pretty lengthy one. We could cover it all in a single video. Okay, so let's literally quickly check this one out. So a linear equation is not always in the form. It can also be like this form or this form and more. Now, these are all the same linear equations. So as long as that the variable is not to the power of something, then you're good. You're in the good linear equation realm. A system of linear equations is when we have two or more linear equations working together. Yeah, that's a system. That's how we call it a system, because we have more than two equations working together. In our system of linear equations, can you discover the value of x and y yourself? Yes, substitution or elimination. So how to build and solve a real-world example. Okay, it's a race. You can run 0.2 kilometers every minute. Horse can run 0.5 kilometers every minute, but it takes 6 minutes to saddle a horse. How far can you get before the horse catches you? So that one has a plus 6 minutes in the equation, so that's a time every minute, right? So let's do 2 kilometers every minute. So that's like 0.2 kilometers multiplied by the minutes. Let's call it D or something. T. And then the other one, 0.5 T plus 6 minutes. We need to add 6 minutes to the mix. And then we know the distance is the speed. Sorry, the speed is the distance over the time. Distance over the time. That's the speed. Since we have the speed, then since we need the distance, then it's speed multiplied by the time. And then we have a solution we need to solve. Now, starts at 6 minutes, but then runs faster. Seems you could get caught after 10 minutes. You only got 2 kilometers away. Run faster next time. Let's try to see what the image has. Didn't load properly. Alright, I think we could solve things from here the next time. We could go from here and see. Alright, see you in the next video. Need to plug my laptop.